In the last video, we learned how to impose stress constraints. In this video, we will learn how to impose design constraints. So we'll start with loading the swing arm model, and this is the swing model that we will use to impose design constraints. For this model, we will apply the alloy steel material. That's the default material. And for the loads and restraints, we will restrain this face XYZ fixed in all the three directions, apply, and we'll apply a force, a vertical force in the negative Y direction of 1500 newtons. Once the force and restraints have been applied, we'll move on to FEA. We'll increase the mesh quality to medium and run a static analysis. Once the static analysis is complete, we will now start looking into design constraints for topology optimization. And to begin with, let's start with the following scenario. As in the previous video, we will try to remove as much material as possible by changing the desired volume fraction to close to 0. We will keep the fixed faces. In other words, we like to retain the material around the restrained faces. And finally, we'll also impose the symmetry along the thickness direction, and we'll optimize. And once again, we'll wait for the optimization to complete. The optimization is now complete, but one of the things you'll notice is that it has pockets in the Z direction. In other words, we may not be able to cast this part easily, given that there are pockets along the thickness. So we'll impose a design constraint now, where we will say the draw direction is Z, and this will avoid pockets along the thickness, and we'll optimize once again. And we'll wait for the optimization to complete. The optimization is now complete, and you'll see that the design is significantly different from the previous design, and in fact this might be more desirable from an aesthetic perspective. And yet another thing you'll notice is that the volume fraction that we were able to achieve is much lower than the previous topology optimization run, and thus there's a significant interaction between some of the design constraints and the stress constraints. Often when we impose the draw direction constraints, the topology optimization can reach a lower volume fraction, but that will depend from one problem to the other. Having completed this design constraint topology optimization, we'll study one more design constraint method. For this method, we will switch over to the geometry display mode, and we'll display the solid part, and we'll hide this one. If you'd like, you can show the loads as well. Now what we're going to do is we will like to impose a design constraints where we do not remove material from three surfaces. So the following design constraints are imposed. We select the top face, the whole surface, and the side face. Oops, we need to start by using the control button, and the bottom face. Once we select these three faces, we'll impose a design constraint that says retain. Essentially what this constraint says is that while we are carrying out topology optimization, do not remove material next to these three faces. And we'll apply, and you should see the constraint being imposed. And now we'll switch over to topology optimization, and we'll keep these options as it is. We'll keep the fixed faces, which is out here. We'll once again impose the draw direction. We want it to be castable in the draw direction, but we will get rid of the symmetry because our boundary conditions are not symmetric. And in fact, the topology will not be symmetric in the z direction. And we optimize. The topology optimization is complete, and you'll find that the topology optimization is in fact very different from what we found in the previous two topologies. And in this particular design, you'll find that you're retained the faces from this direction. From an aesthetic perspective, this might be desirable, and it creates rib structures on the inside to result in a different topology of a different volume fraction. And this concludes our video on design constraint topology optimization.